Hi, so welcome back to our training series. So today in this session, we are going to talk about the part 2 of the searching. So last week, we have talked about so for the last week, we have talked about complete search and greedy search. So for this week, we are going to talk about divide and conquer. So the philosophy behind divide and conquer is to divide the problems into sub-problems, solve the sub-problem and combine the results together. So the nice symbol would be merge sort. So let's see how merge sort works. It is a and sorting algorithms. So which is fast. So this is the animation of it. First we divide. Again divide. So and if you note, each time we are dividing the elements into half. After dividing them, then we sort them. So in this case, I have one element on the left and one element on the right. So I sort 3, then 5. So the next sorting would be among these two groups. So in the end, we'll eventually merge everything together and this array will be sorted. So this is a simple example of it. So the next thing is that, in fact, we have two methods in order to tackle the problems. The first method is binary search and the second method is bisection method. So for the binary search, simple is which I will talk later. So for the whole idea, divide and conquer is actually a n-ary search tree. For our case, they are binary search tree. So I have left and right. So effectively, on each level, I will split the data into half. So it is binary. So if we fan out into 3 elements on each level, then it will be a ternary search tree, but we are not talking about it here. So first part, binary search tree. So just a simple revision, how to, given you a 10 random numbers, if you want to find a numbers from number array, so how will we find? If we use linear search, it will be ON. But if you use binary search, it will be, so some errors here, it will be O log N. Why? So this is the pseudocode here, but we will come back to it later. So let's see the example. We have this array 3, 4, 7, 8, 100, and 500. So at the starting point, get of this array. So the length of this array, the maximum array index of this array, 0, 1, 2, 3, 4, and 5, which is here. So I get my mid, which is 2. So the value I get is 7. So the next thing, if the value we want to find is less than 7, then we go left. Otherwise, we go right. So it is quite similar to the binary search tree illustration is quite similar to the what you have taught by the lecturers. So if you want to find 4, then we will go 7. So 3 is less than 7, then we go left, which is the left half. So it ranges from 3 to 4. So we compare 4 against 3, and we found that 4 is larger than 3. So we go right, which is the upper range of the smaller array. So previously we have 3 and 4. So now we want to find the upper range. So it is 4. So we compare 4 with the elements in the mid of the range. So which is 4 because it is one element in the sub array only. So we found that. So another example, if you want to find 8, so initially we have 7 as our mid, then we compare 8 to the 7. So we found that, okay, 8 is more than 7. Let's just go to the upper part of the array, which is 800. So we are at this stage now. Next, so the mid is 4 now. So we compare 8 to 100. 100 is more than 8. So this should be 8. Okay. So 100 is more than 8 to the lower range of this subarray, which is from 500. It the 100 and found okay. So 8 is less than 100. So the next range will be 8. This is 8 by itself. If you have more array, you might get lower or deeper layer. So now we left 8. Our minimum is 3, maximum is 3 for the index, and our mid is 3. So we compare the target we want to search, the mid of the sub array again. So okay, at this stage we found that 8 is actually the one we want to find out. So we found it. The next, if we couldn't find 2, so our value in the initial value is 7. So maybe I just copy this over here. So initial our range is here. So we compare the value. We found that 2 is less than 7. So our range will be here. 0 plus 1 divided by 2 is 0 in terms of integer. So we check 3. So we compare 2 with our current mid, which is 3, and we found that 2 is less than 3. So we go left again. We will found that, so our mean is equals to 0 at this stage, and x is equals to 0 at this stage. And we found that if such condition exists, mean less than or equals to max, so the result should not be found. We cannot find any values in the array. So that is it for binary search. So let's go back to the code. So this is a recursion star code. First, we have minimum, which stands for the minimum array index, and the maximum, and which stands for the maximum array index we want to search. In this case, is our range. So while min less than max. So while our condition is not met, min more than or equals to max, as still trying to get the value, we have not encountered the problem that we can't find our target value in the array. So this is our mid. Min plus max divided by 2 is our mid. If the value at the mid is equals to a target, which is the target we want to find, then we maybe just return the value or a flag. That's up to you. Else, if the mid is not the value we want to find, then we check it. If array is mid is more than target, so in this case, let's say we want to find 4 at our stage, we are at 7. So if 7 is less than the target we want to find, so we'll reduce the range from 0 to mid minus 1, which is 3 and 4. Otherwise, the value is larger. So let's say we want to find 100. So we compare 107 and we found that 100 is more than 7. So we will reduce our range to mid plus 1, which is from 8 index. And we do the loop again until we either get not found or we found the value. So which is a condition here. So let's analyze it. For linear search, it works for any array. Search, it works for sorted array only. Because the reason behind this is cutting down the range by half in order to find the value. So we have the concept of, okay, our target is actually lying somewhere in the, so we have a knowledge on that. So for small n, linear search is faster. For big N, binary search is faster. The issue lies with small n about linear search is faster if happens to be at the front. Let's say if I have to search 3, for linear search, I will go through first one. Is it a value? 3. So it is the value we want to find. So we found it. We need to do in order to find the first element in the array list is, but for binary search, do 2 operations. But how about if the value is at the last of the array, then we got to go through n values or n elements in the array. So this case, linear search is slower. For binary search, if you want to find 500, we just need to do the operation 3 times. For linear search, we need to do n times. So in this case, elements, so we need to do six operations in etc. like compare. So if you are doing a lot of searching, so please sort it first. then you can use binary search as you want. So the main issue is low as initial state. Case we can use quick sort or merge sort. Those sort with log n complexity, then it will reduce the impact of it. But when you do a lot of searching, the actual time spent on this sorting is overwhelmed by the speed up in the binary search. So this is the nice graph. As you can see, it scales linearly. But for binary search, it scales logarithmically. So this is the sample questions we are going to discuss. The question is exact sum 11057 in UVA. Peter received money from his parent this week and wants to spend it all buying books. But he doesn't read a book so fast because he likes and enjoy his reading, probably literature books. It takes him a week to finish a book because instead of understanding the book, he reads every single word. As Peter receives money every 2 weeks, he decides books, each book 1 week. Then he can read them until he receives more money from his parent. As he wishes to spend all the money, he should choose 2 books whose prices sum up are equals to the money that he has. It's a little bit difficult to buy these books, so Peter asks your help to find them. So each test case starts with n, the number of available books. The next slide will have n integer representing the price of each book. A book costs less than million of one, and then there's another line with integer m representing how many money Peter has. So there's a blank line after each test case. So let's see the 7. So this is the available books, which is 2 in this case. Then we should expect 2 prices on the following line, and the next line will be the money that he received from his parent. For this, after a blank space, we have 5 books to choose from, and these prices are the book prices, and this is his money. So it's quite pity of him that he received $10 for the 2 weeks. So for let's see the output for each test case. You must print the message. Peter should buy books whose prices are 1 and J. So it's I and J. So where I and J are the prices of the book whose sum is equals to M, and such that I is less than equals to J. So you can consider that it's always possible to find a solution. If there are multiple solutions, print the solution that minimizes the difference between prices I and J. After each test cases, you must print a blank line. So let's check out the sample output. For this case, we have no choice but to choose both 40-40. And we consider the solution is always possible from the input data. So we should not worry about that. For test case 2, we have 5 books to choose from, and there are 2 possibilities in this case, 2 and 8. which sum up to 10, and 6 to 4, which sum up to 10, 2. The question demands that we minimize the difference. So the difference between 2 and 8 are 6. The difference between 6 and 4 are 2. So we should pick 4 and 6 instead of 2 and 8. Okay. Mm-hmm. We don't bother this first. So we start walk through look for test cases. Integer, the first line, options count equals to the number of books we can choose from. So the next line, prices, count. I think we can use an array list. Yep. Or even better, we can use hash map. So integer options. So for this thing, we can actually ignore it. We just call a read line. It doesn't really matter. End up it matters for because we need to count the things. I less than options count I plus plus. So options dot put. We need a string tokenizer to read the next line. I'm going to put it outside of the loop because it is on the same line for the prices. Integer dot pass integer. We convert the price of the books. Options dot get or default value 0 plus 1. So what I'm doing here is actually putting the counter for the value of the book. Let's say I have counter for the books value 2, so the counter should be 1, and 6 should be 1, and so on. If we have 2, then it should be 2. So I will show this first. Later we will go to the binary search method. Okay, so we have got this. Then we'll go through the values. Key. So these are our keys. And the next thing I want to put here is the sum. Hang on, sir. So we have the
ต้องก็เป็นโถเสร็จ
huh?
ต้องก็เป็นโถ
and so the value